Okay, so using technology, graph y equals x to the power of 3. And then you're going to sketch the graph of if we translated it down 2 units and then stretched it by a factor of 3. Okay, for b, you're going to use the same parent function, y equals x cubed, but you're going to stretch it by a factor of 3, then translate it down by 2 units. So we'll see what that means in terms of difference. So I'm not going to flip to the decimal screen because I already am familiar enough with my parent functions to know that my cubic looks something along the lines of that. That's a very rough sketch. It should be symmetrical around my line x, y. But it gives me that general idea, and it gives me my points of -1 and or 1 and 1, -1, -1. So if I shift it down 2 units first, all of a sudden I'm getting a point here. But then I have to, maybe if I do mapping notation, that would help. So f of x, parent function, down 2, and then stretched by 3. So originally I'm at -1 and -1. That doesn't look -1 at all. Got 0 and 0, and I've got -1 and or +1. And to move them down 2, I would go -1 and -3, 0 and -2, and 1 and -1. Then to stretch it vertically by 3 means then I'm going to be looking at, okay, well, multiplying my y value by 3. And I don't think it says specifically stretch. Oh, the first one says vertically. So assume we're doing vertically for both. So I would multiply this value by 3. So I've got -1, that's still unchanged, but now I'm working with -9, 0 and -6, and a 1 and -3. So let's try and imagine that. Working with some funny numbers here. So I'm having to go down to -9, so I'm going to be pretty picky about my negative x-axis. 3, 6, 9. I'm going to spread out my 1 just so I can kind of see it. -1. Okay, so when I go to graph this, I'll zoom out a little bit. My parent function, again, just to kind of give me a point of reference, is here, here, here. So my graph is going to look like this. Oh dear. Okay, so imagining that I'm really struggling with this. There we go, that looks better. Okay, so we've got our parent graph, f of x. But then when I go to graph this next one, it should look the same, just vertically skinnier and moved down by 2. What I see here is I go to -1 and -9. Okay, so that looks like it's moved way down, and so it might be stretched. 0 and -6. So right here. And then a 1 and -3. Well, no matter which way you look at it, like maybe it's stretched by 3, but there's no way you can argue that this is actually moved down by a factor of down 2 units only, because I've gone from 0 and 0 to 0 and -6. This is too much. So something funny is going on. But I swear I did it right here, like I promise you. So if we look at B, it says do the factor of 3, then move it 2 units down. So let's see what happens there. We'll do the same setup using our mapping notation. Times 3, and then down 2. So -1 and -1, 0, 0, 1 and 1. I like cubics for that reason. It's easy to work in the middle. Okay, so times 3 would get me -1 and -3. 0 and 0 becomes an invariant point, 1 and 3. So we see some symmetries here where we didn't see it necessarily as much there. Then we go down 2 from there, so -1 and -5, 0 and -2, and 1 and 1. And so already this is looking maybe a little bit better, but let's graph it just to be sure. So I'm going to spread out my points a little bit more because I can. Again, I'm going to keep my 1s pretty spread out because I have lots of opportunity to. So to graph my parent function again, I'm going to just sketch it in real quick. But for my new function, I'm going to go to -1 and -5. Go to 0 and -2, and 1 and +1. There we go. So zooming out again so that we can see both these at the same time. Which one looks like it's stretched by 3 and moved it down 2? Well, I would say this one for sure. It looks like it's moved down way more, and like I can't really tell where to look to tell how much it's moved down. Whereas here, I know specifically that my x-intercept should have been an invariant point when I multiplied. And it's not an invariant point when I multiply here. So that tells me that method B is the method to use. In general, the rule is stretches and compressions first, then translations. Okay? So if you need to note that, take a second now, write that down. Okay, just off to the right here in our OneNote, I do have this kind of summary of how all the different transformations look in terms of reference to the parent function, their descriptions, and also how to do it using mapping notation. So if you need to refer back to that, copy it down, whatever you need to do that. If you don't need it, great. It's also summarized here. So always do horizontal stretch compression and vertical stretch compression, followed by translations. So we're seeing that here, just summarized even more succinctly up here. So then when we see it in terms of our mapping notation, that shows up in that we're going to do our multiplication and division, so working with A and B, and then implementing C and D. That'll be the order that they're implemented. Okay, so this is the general transformation. So again, when we throw all 4 things potentially at you at once. So that's kind of the notes on that. There's lots of practice worksheets. So you've got this one here where you're going to be graphing lots and answering a couple questions. Then we've got this worksheet here, which kind of throws it in perspective, like for all the different ones. And there's an answer key for that one. I really, really, really like this one. So again, it summarizes all of your different transformations here. They use K instead of B, so that would be the only difference. And you'll see that used interchangeable, or sometimes see that, not really though. So K is B, just note that. And I like all of these questions. I was a really big fan of this worksheet. My favorite part though is this last page because it encourages you to use your mapping notation to alter that 1 point, and then also for each of the following, name a point on the graph and then the transformation. So I would use this point, and then you're going to state the new point and tell me the transformation. So is it a reflection? Is it over the y-axis, over the x-axis? Is it a translation? Is it vertical or is it horizontal? Left or right? Up or down? Is it stretch or compression? Vertical or horizontal? Okay, so I really like this last page on this last worksheet. So if you are feeling like, well, this worksheet is great and I don't really need to do this one, please jump to 4.3 and do this last page because I am a huge fan. That'll be a really big advantage for you to be able to like really settle into that. And it takes us back to the individual transformations as well. So some good practice there. But yeah, so that's our last lesson on transformations in their most basic sense. Our next lesson looks at inverse relations, which is technically a type of reflection, a type of transformation, but it's going to look a little bit different than what we've been seeing so far. So up to this point, it's been a lot of what we talked about in our trig unit, but we're going to start doing some weird stuff in the next one and our last 5 lessons. So do lots of practice questions. I'm going to be posting an assignment for stretches and reflections if I can find enough questions that kind of work with just those two. Otherwise, I will definitely be posting an assignment that will be combining all of our different types of transformations. So that'll be coming soon. And again, please always remember that if you have questions, email me.